Hello, my name is Brandon Fetter. In a previous project, I created a Mandelbrot Set zoomer that utilized all 16 threads of my CPU. However, since then, I've gotten an NVIDIA GPU and wanted to redo the project using the more than 2,000 cores that I have access to. To start off, I created a new folder to house my project files, opened my IDE Atom, opened my terminal, and most importantly of all, opened my web browser. Then, I found some starter code for PyCUDA, the Python implementation of NVIDIA's CUDA library, though I ended up using Numba, a Python compute library, later. Then, I installed and set up Pygame, which I will be using to draw the Mandelbrot set to the screen. I also created a new file to house the settings. Next, I set up some functions to program, such as the one that will get the Mandelbrot set values and read it into a buffer. Then, to keep the project neat, I added some comments and a file to hold helper functions. For the next 20 minutes or so, I started setting up the C++ code that would act as the NVIDIA CUDA kernel. I also programmed the function that would call the kernel and read and put the values into a buffer to be drawn to the screen. Here is the result. At this point, I set up a few lines of code to calculate the FPS. Unfortunately, I was getting about 1.7 frames per second, which is way too slow. After confirming my suspicions that it had to do with the code I borrowed from the PyCUDA documentation required copying the array of more than 1 million pixels twice every ideally 16 milliseconds was not going to work, I did some major efficiency improvements. Some of these included switching the Pygame function I was using to render the pixels to the screen, and removing one of the buffer copies as it was not necessary. I managed to get just under 200 frames per second. While doing these changes, I also started playing with the data type of the pixel buffers I was passing to the GPU. I was originally going to use NumPy's 80-bit double, which is equivalent to C's long double. However, my GPU only supports up to 64-bit doubles, which is equivalent to C's normal double, meaning that it was not going to happen. In the process of doing this, I messed up, and this is the result. It took me a very long time to resolve this issue. However, in hindsight, it should have been obvious. What happened was that the NumPy array I was using to store the pixel buffer that was being passed to the GPU stored 64-bit integers, while the array the GPU was accepting stored 32-bit integers. Therefore, because the 32-bit array will take up half the space, only half the 64-bit array was being written to. I ended up using these integers opposed to doubles because it made much more sense to store the Mandelbrot set data as integers. Next, I set up the function that colors the pixels based off their Mandelbrot set values. I was having performance issues with this, so I used Numba's JIT directive to speed it up. When I was doing this, I learned that Numba provides CUDA support. The next bit of time was spent programming the PyCUDA kernel that would never be used, so I won't go into details about that. After getting more and more frustrated with using PyCUDA, I finally decided to use Numba for the GPU, which was probably for the best anyways, because it means I have one less library to worry about, which is always good when working with complicated projects. Now is when I started programming the most important part of this program, the actual calculation of whether a point is in the Mandelbrot set. Overall, it went pretty smoothly, but there was one instance when I had trouble. I was trying to do the calculations recursively, but was having trouble with Numba, so I decided to do it iteratively, which I think was more efficient anyways. After only a few minutes of finishing the iterative calculations, I got the visualization working, as you can see here. The rest of the time was spent programming movement, zoom controls, and tweaking different variables to make the program more efficient and easier to use. I also spent a good chunk of the time playing with my new baby. One of the hardest parts of this was finding the correct max depth to calculate each coordinate with as a function of the zoom. I settled on about 2 times the natural log of the zoom, but the base can be changed by the user. One issue that I am not going to resolve in this project is that because of the limited accuracy of NumPy's double, once zoomed in far enough, effects like this occur. Lastly, I made some final tweaks involving the function to determine the max depth, movement speed, etc. Here's the final result with super dramatic background music.